episode 32, titled GENEVE, where encapsulation shows up and what it implies, we treat generic network virtualization encapsulation as flexible encapsulation for modern overlay networks, because many contemporary data center and cloud designs rely on tunnels even when the word tunnel never appears in the requirements. The exam is less likely to test you on packet header trivia and more likely to test whether you understand what encapsulation changes about visibility, policy enforcement, performance, and troubleshooting. Generic network virtualization encapsulation shows up in environments where tenant traffic must traverse shared infrastructure while remaining logically separated, and where carrying extra context about traffic can help enforce microsegmentation and service chaining. When you recognize that encapsulation is present, you stop assuming that what you see on the wire is the original traffic, and you start asking where the inner flow is defined, where it is enforced, and where it is observed. That shift matters because many mysterious outages are really tunnel issues, such as maximum transmission unit mismatches, underlay instability, or missing visibility into inner flows. The goal of this episode is to make you fluent in what encapsulation implies so you can reason quickly when a scenario hints at overlays, tenant isolation, or hidden traffic paths. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Encapsulation exists because it allows tenant traffic to be carried across shared infrastructure without forcing the underlay to understand every tenant's segmentation, addressing, and policy. In a shared fabric, multiple tenants and multiple application environments may need distinct logical networks, but building separate physical networks for each is expensive and difficult to scale. Encapsulation wraps an inner packet, which represents the tenant or workload traffic, inside an outer packet that the underlay can route like ordinary transport traffic. The underlay then focuses on delivering the outer packet between tunnel endpoints, while the overlay endpoints handle the inner delivery into the correct logical segment. This separation enables mobility because workloads can move while the logical network remains consistent, and it enables scalability because the underlay remains a clean Layer 3 system rather than a sprawling Layer 2 domain. In exam scenarios, when you see multi-tenant requirements, segmentation across racks, or overlay connectivity across a cloud fabric, encapsulation is usually the mechanism, even if it is not named. The practical takeaway is that encapsulation is a technique for decoupling logical networks from physical transport so both can scale independently. One distinctive implication is that metadata fields can travel with the encapsulated traffic, enabling policy decisions and service chaining that are difficult to express purely with outer addresses. Metadata can carry context such as tenant identifiers, segment identifiers, or other classification signals that help enforcement points make correct decisions even when the underlay addresses are generic transport endpoints. This matters in microsegmentation designs where policy is based on workload identity, environment, or application role rather than on raw Internet Protocol addresses alone. Metadata also supports service chaining, where traffic is intentionally steered through a sequence of network services such as inspection, filtering, or logging components based on policy intent. The exam is not asking you to memorize exact field names, but it does expect you to understand that modern encapsulation can carry extra context that influences how the network treats a flow. When a scenario describes policy decisions based on tags or steer traffic through security services, metadata-aware encapsulation is often part of the underlying design. The core idea is that tunnels are not only about transport, they are also about carrying intent. Conceptually, it helps to contrast encapsulation approaches with other tunnels by emphasizing flexibility over specifics, because the exam often tests your understanding of the idea rather than of a single implementation. Many tunnel mechanisms exist, but the common theme is that they wrap an inner packet inside an outer transport so traffic can traverse an intermediate network that does not participate in the inner addressing and segmentation. What distinguishes flexible encapsulation approaches is the ability to carry variable or extensible metadata, allowing the overlay to evolve without redesigning the underlay. This flexibility matters in cloud and data center environments where requirements change, policies evolve, and new services are introduced regularly. The practical reasoning skill is to recognize when you are looking at a two-layer network where the underlay sees one set of headers and the overlay logic cares about another. When you adopt that two-layer lens, you stop debating which tunnel is best and start focusing on what the tunnel implies for routing, policy, and observability. In exam scenarios, the best answer often reflects this lens by addressing underlay health, maximum transmission unit planning, and visibility into inner flows rather than obsessing over protocol branding. Encapsulation awareness is especially valuable for troubleshooting and maximum transmission unit reasoning because tunnels add headers and change what packet size means on the wire. When you encapsulate, the outer packet includes additional header bytes, making the transmitted size larger than the original inner packet. If the path maximum transmission unit is not sized to carry the encapsulated packet, you can see fragmentation, drops, or intermittent failure patterns depending on how devices handle oversized packets. This is why tunnel issues often show up as small requests work but large transfers fail, or as performance degradation after enabling an overlay, even when the underlay looks fine for ordinary traffic. Encapsulation also changes where to look for failures, because a tunnel problem could be underlay routing, tunnel endpoint configuration, or policy at the encapsulation boundaries rather than inside the application. In exam terms, when a scenario mentions overlays and intermittent failures correlated with payload size, maximum transmission unit and encapsulation overhead should move to the top of your reasoning stack. The key is that tunnel overhead is not an edge case. It is a predictable design constraint that must be accounted for. Performance implications follow naturally because added headers increase overhead and raise fragmentation risk, which can reduce throughput and increase latency under load. Overhead means a larger portion of bandwidth is consumed by headers rather than by application data, which matters most when traffic volumes are high and when links are close to saturation. Fragmentation risk matters because fragmentation increases processing work and can cause drops when fragments are filtered or mishandled, and drops can trigger retransmissions at higher layers that appear as application slowness. Encapsulated paths can also add processing at tunnel endpoints because encapsulation and decapsulation are additional steps that must be handled efficiently. In modern designs, these costs can be managed, but they are still real and should be considered in capacity planning. The exam may express this as performance degraded after enabling overlay, or throughput lower than expected across the fabric, which should trigger awareness that encapsulation adds overhead and can reveal maximum transmission unit inconsistencies. A well-reasoned answer accounts for both underlay capacity and overlay overhead rather than assuming overlays are free. The main lesson is that performance in tunnel designs depends on healthy transport and consistent packet sizing, not just on bandwidth numbers. Security implications matter because inspection points may miss inner headers, meaning traditional controls that inspect only the outer packet can lose visibility into the actual application flows. If a firewall or monitoring tool sees only outer tunnel endpoints, it may be blind to the inner source and destination, ports, and application context that determine whether the flow is legitimate. This can create a security gap where policies are enforced only at tunnel endpoints and not throughout the path, which is fine if designed intentionally, but risky if assumed to be equivalent to full visibility everywhere. It can also create a logging gap where all traffic appears to be between a small set of tunnel endpoints, making it hard to attribute behavior to specific workloads. In environments that rely on segmentation and least privilege, you must ensure that policy enforcement is applied at the correct layer, often at the overlay edges or through metadata-aware controls, rather than assuming the underlay can enforce tenant policy. The exam often tests this by presenting options that place inspection in the underlay without acknowledging that inner flows are hidden, which is usually incomplete. The best answer typically emphasizes controlling and observing at the tunnel endpoints or using tools that can interpret inner headers. The key is that encapsulation changes what is visible, and security design must follow visibility. Consider a scenario where an overlay carries microsegmented traffic across cloud fabrics because it illustrates why encapsulation and metadata matter in modern architectures. A set of workloads may be split into fine-grained segments based on role and sensitivity, and those segments must remain isolated even as workloads scale across multiple nodes or across multiple physical locations. Encapsulation allows those workloads to communicate within their logical segments while traversing a shared underlay, and metadata can carry the segment or policy context needed for enforcement. In this scenario, the underlay focuses on reliable delivery between tunnel endpoints, while the overlay and its policy system enforce which microsegmented flows are allowed. Troubleshooting focuses on both layers, underlay reachability between endpoints, and overlay policy correctness for inner flows. In exam reasoning, answers that mention overlay segmentation, microsegmentation, and policy tags often imply flexible encapsulation, and the best response is to ensure both visibility and enforcement exist at the right places. The practical message is that microsegmentation at scale often depends on overlays, and overlays depend on consistent transport and correct policy distribution. A common pitfall is monitoring only outer headers because that hides inner application flows and can make both troubleshooting and incident response far harder than they need to be. If all you see is traffic between tunnel endpoint addresses, you cannot easily tell which workload initiated a connection, which service was targeted, or whether the flow violates policy. This can lead to misdiagnosis, such as blaming the wrong application tier because you lack the inner context needed to correlate failures with specific services. It can also reduce detection capability because lateral movement inside the overlay can be invisible if your monitoring collapses everything into endpoint-to-endpoint flows. The remedy is not necessarily to monitor everywhere, but to ensure your logging strategy captures both tunnel endpoint details and inner flow identities where they matter most. In exam scenarios, when the prompt mentions loss of visibility after enabling overlays, the best answer often involves improving telemetry to include inner flow context and ensuring policies are enforced close to workloads. The key is to treat observability as part of the architecture, not as an afterthought. Another pitfall is inconsistent maximum transmission unit across the path because it causes intermittent failures that are workload dependent and difficult to reproduce. When maximum transmission unit is inconsistent, Some nodes may send inner packets that, once encapsulated, exceed the underlay limit, causing drops or fragmentation that appears only for certain applications or payload sizes. This is why some services work while others fail, and why the failures may correlate with file size, response size, or specific protocols that generate larger packets. These symptoms can be especially confusing because basic connectivity tests may succeed, and only certain operations, such as large transfers or specific transactions, fail repeatedly. In exam reasoning, this pattern should push you to consider maximum transmission unit planning and validation in encapsulated networks rather than chasing application settings first. The best answer typically involves ensuring a consistent maximum transmission unit end-to-end that accounts for encapsulation overhead, because that removes a whole class of intermittent problems. The underlying lesson is that tunnels amplify path maximum transmission unit sensitivity, so consistency is essential. A quick win is to ensure logging captures both tunnel endpoints and inner addresses, because that provides the minimum context needed to correlate behavior and diagnose failures in encapsulated environments. Tunnel endpoint logs tell you which underlay devices are involved and help you identify whether the transport path is unstable or congested. Inner address and port context tells you which workload-to-workload flows are affected and whether policy enforcement is blocking or allowing as intended. Capturing both contexts also helps incident response, because you can attribute actions to specific sources even when many flows share the same outer endpoints. This does not require inspecting everything everywhere, but it does require deliberate selection of observation points that can see inner flows, such as overlay gateways, host agents, or metadata-aware monitoring components. In exam scenarios, when a question implies that troubleshooting is difficult because traffic is encapsulated, the best answer often includes improving observability at the overlay boundaries. The practical point is that tunnel designs require layered logging that reflects layered reality. Without layered logs, you are blind to the real traffic while staring at the transport wrapper. A memory anchor that keeps this straight is tunnel, metadata, policy, and visibility all connect, because these are the four elements that define what encapsulation changes in practice. Tunnel reminds you there are outer and inner headers, and that the underlay carries the outer while the overlay defines the inner. Metadata reminds you that additional context can ride with the traffic and influence how it is treated, especially in microsegmentation and service chaining. Policy reminds you that enforcement must be placed where the relevant information is visible, often at the overlay edge or with metadata-aware controls. Visibility reminds you that monitoring must include inner context, or else troubleshooting and security detection degrade dramatically. When you can recite this anchor, you can interpret scenario questions about overlays and encapsulation without getting stuck on protocol branding. It also helps you prioritize, because when tunnels fail, you immediately think underlay health, maximum transmission unit, endpoint policy, and observability. This anchor is a practical roadmap for both design and troubleshooting. To end the core, list 3 things to check when tunnels fail, because this is the exam-ready way to turn encapsulation awareness into action. First, verify underlay reachability and stability between tunnel endpoints, because without stable transport, the overlay cannot function reliably. Second, verify maximum transmission unit consistency across the path, accounting for encapsulation overhead, because size-related drops and fragmentation create classic intermittent symptoms. Third, verify that you have visibility into inner flows and that policy enforcement at the overlay boundaries is behaving as intended, because a tunnel can be up while inner traffic is blocked or misrouted by policy. These checks separate transport problems from overlay logic problems and reduce the time spent chasing the wrong layer. In exam scenarios, answers that begin with these fundamentals tend to be correct because they reflect the layered dependency model of encapsulated networks. The key is that tunnel failure is rarely a single knob. It is usually a layered issue that must be isolated systematically. In the conclusion of episode 32, titled GENEVE, where encapsulation shows up and what it implies, the main lesson is that flexible encapsulation allows tenant traffic and micro-segmented flows to traverse shared infrastructure, but it changes performance, security, and observability in predictable ways. Encapsulation exists to carry inner traffic across an underlay, and metadata can carry context that supports policy decisions and service chaining across boundaries. Added headers create overhead and maximum transmission unit sensitivity, and inspection points that see only outer headers can miss inner flows, creating visibility gaps and potential security blind spots. You avoid pitfalls like monitoring only outer headers and inconsistent maximum transmission unit that produces intermittent failures, and you gain quick wins by logging both tunnel endpoints and inner addresses for correlation. You keep the anchor tunnel, metadata, policy, and visibility all connect because that is the essence of what encapsulation changes. Assign yourself one tunnel troubleshooting rehearsal by choosing a simple overlay scenario and walking through underlay stability, maximum transmission unit planning, inner flow visibility, and policy enforcement in order, because that sequence is how you turn encapsulation from mystery into a controlled, diagnosable design element. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.